Chapter 3, Exercise 19. Hints. Recall the construction of the Cantor set from section 244. See solution to the exercise 217. Solution. Recall that the Cantor set P is defined as this, where E0 equals this. En is a union of 2 to the power n pairwise disjoint segments, and En plus 1 is obtained from En by removing the middle thirds of 2 to the power n segments, which constitute En. We start by finding an explicit form of En. Let In be the set of sequences here, such that each alpha j is 0 or 2. For each sequence here, consider a segment here. We note that E1 equals this. Assume that En equals this. Let us check that in this representation, 2 to the power n segments are pairwise disjoint. Assume that sequences here and there from In are distinct. Let m be the first index such that alpha m does not equal beta m. Without loss of generality, let alpha m equals 0, beta m equals 2. Then we have the following. And continuing. The right endpoint of the segment here is strictly less than the left endpoint of the segment here. In particular, segments are disjoint. Now we obtain En plus 1 from En by removing middle third of each segment here. Points that divide the segment into 3 equal parts are the following. So En plus 1 equals this. And continuing, it follows that En equals this for all n equals 1, 2, and so on. Note that by construction we have this. Consider a point x in P. For every n greater than or equal to 1, there exists a unique sequence here such that this. Let us prove by induction on n that for all k equals 1, 2, and so on to n, we have the following. The base case n equals 1 is obvious. Here. Assume that the statement of induction is proved for n. If 1 less than or equal to k less than or equal to n, then this. If this, then segments here and there are disjoint, which is not the case. So we necessarily have this. Denote the following. Then we have this for all n equals 1, 2, 3, and so on. In particular, this. Taking the limit n to infinity, see theorem 320d, we find that this, where a equals this. Conversely, let x equal the following, where alpha k is 0 or 2. For each n greater than or equal to 1, we get, see theorem 326, the following. That is this. It follows that x in P and the Cantor set P coincides with the set of numbers of the form here, where each alpha k is 0 or 2. Comments. Below, we depict the first 4 steps of constructing the Cantor set P. The first 4 steps of constructing P. The mapping here is a one-to-one correspondence with the set of all infinite sequences of zeros and 2's onto a Cantor set. From this, one can deduce that the set P is uncountable, and in fact, P has the same cardinality as R. Thanks for watching.